Sorry, I'm doing that stupid thing again of not having it plugged in. That's why there's no signal. God dear, Stephen, come on. How embarrassing. There we go. Alright, let's continue. DIFC, physics, materials, specific heat capacity. What did we finish on last time? What was the last thing I did with you?
The table. Yeah.
The table, was it? Okay, great. Right, so let's continue from the table then. We did that. We did this. Oh yeah, so why do different materials have different heat capacities? The answer is it's complicated. And we might look at it later. So you might be wondering, why does water have 4,000 and milk has 2,000 and air has 1,000? The reason's actually quite complicated. When I was looking this up online, I thought there might be a simple explanation, but actually the explanation is quite complicated. Okay, let's do this one together now. How long would it take to boil enough water to make a cup of tea? And imagine you have a small 1 kilowatt travel electric kettle. And I tell you to estimate the initial temperature of water and how much water you would need. So let's do this one together. The question is how much... Where's my pen? It's not working. What I want you to write down is, firstly, just write down how much water you think you need to put in the kettle to make a cup of tea, the initial temperature and the final temperature. So let's just try and do a real life example, okay? So how much water will you need to put into the kettle?
500?
I'd say at least 500, yeah. So what is the mass of that 500 milliliters of water?
500.
500 grams. Now we should use kilograms, so if everybody can write down mass equals 0.5. Okay, got that? Now if you think about putting water in the kettle, what would you say the initial temperature is? Not in Ireland now, come on. You know how cold the water is when it comes out of the taps. Think about turning on the cold tap and putting your hand under it now. I promise you it's not 25. Come on! How long have you been in Ireland now? 10, I'd say. So, probably 10 Celsius. Yeah. And what temperature are you trying to get the water to? 100. Good. So, what is the delta theta here? 90. Okay, and what's the mass? We said it was 0.5 kilograms. Okay. And what's the power? It's 1,000 watts. Okay, and we want the time. So, power equals work over time. So, time equals work over power. Now, we know the power. But what's the work here? What work are you doing? What's the work here?
Q.
Well, the work is heating the water, isn't it? So what's the formula for the energy you need to heat the water? What's the formula? M C delta theta. Got that? Yeah, this is using MC delta theta. Okay, take out your calculators and give me the time, so, yeah?
How do we know if we need to use Celsius or Kelvin?
It doesn't matter. Because you're always looking at delta theta. You're never looking at theta. the temperature. So in fact, strangely, it doesn't matter if it's Celsius or Kelvin, because since you're only looking at differences, it'll be the same. So this actually is the same as 90 Kelvin as well. We have an answer?
Yeah.
Yeah, what's the time? 188 seconds. Yeah, now that's seconds, so we should change that maybe into minutes. So what's that, about 3 minutes and 8 seconds? Yeah, 188 seconds is 3 minutes 8 seconds. Which seems like, you know, a reasonable answer. Does this make sense? It's not too difficult, I hope. Shall we do another example, maybe? Or? Yeah? Let's scroll down. Can I scroll down? Does anybody have their phone handy? Can someone just take a Google? I just would like to know for this example how much water a shower uses. So when you take a shower, how much water do you use? So I want to calculate how much energy you need to take a shower, because you have to heat the water, and it's actually a lot of water. No, don't distract him. He's getting me something on Google now.
65.1 liters.
That's a lot. That's a lot. Right. Guys, can we do another example? Yes? Okay. Okay. There we are. We've got our brush. We've got our shower cap on. We've got our shower. Ready, guys? Are you not getting the right answer over there?
I'm guessing 3.13
For what?
minutes.
Yeah, that's fine. 3.13 minutes. It's the same thing as 3 minutes and 8 seconds. Because there's 60 seconds in a minute. So 0.13 of a minute is 8 seconds. Yeah. Okay, so here we are. Our friend here is taking a shower, and according to you on Google, he will use 60... Okay, so let's just say 65 litres then. So use 65 litres of water. So what's the mass here? It's kind of a lot, isn't it? What is it? 65 kilograms. Fine, okay. Now, just like with the kettle, what would you say the temperature of the water is when it goes into the tank? Well, it'd be about 10, wouldn't it? And what temperature are you trying to... What would be a reasonable temperature for a shower? I don't know. What do you think? What would be a reasonable temperature?
60?
30? 60? That would burn the skin off you. 30, you think? I think 30 sounds a bit chilly, maybe. I think about 40, maybe. So we'll say delta theta is about 30 then. Yeah? Now, what I would like you all to calculate quite simply is just what is the energy required here using MC delta theta. Okay, so tell me what you got. Answer? 8, 1, 2950. Okay, we should put that into, is that megajoules? Yeah. 8.15 megajoules. It's a lot, isn't it?
Yeah.
Yeah? Now I can actually tell you how expensive that is. I think now in Ireland the way the price works and in most countries is what they call it what the electrical company calls 1 unit of energy is in normal units for us is 3.6 megajoules. And that would be about, oh my goodness, what is it about? Like something like 16, 17 cents. You have Google there. Type in Ireland price 1 unit of electricity. See what we get. I think it's something like about maybe 17 cents. Maybe. Compared to other European countries, it's a little expensive. So we could actually work out how much the shower would cost. It would be, well, how would you calculate it here? How much is it?
It says cents per
unit, kilowatt hour.
Yeah. 16.57.
16.57. Hey, I wasn't so bad there. 17 cents. But I think you might have to put tax on that as well.
Oh, it's 16.97.
Including tax or not? It's probably not including tax. So we'll say it's 20 cents. Okay, so how would we get the cost here? It would be 8.15. What would you do? Over. Yeah. By.
0.2.
Yeah, so what does that come in as?
0.456.
Yeah. Yes? Now, multiply that by 30. What you get? 13.58. So that means when you get your electricity bill once a month, 13 euros of that will be from just using the shower.
Why do you need to
Times by what?
Oh, okay, that's my everything.
Oh yeah, I just wondered, like on your monthly electricity bill, how much of it is because of the shower? It's about 13 euros.
Why by 30?
Oh, because I want to know how much per month. Because you get your bill every month. So I wonder how much it would be on the bill. Huh?
You shower
Once a day for 30 days. Yeah. What's confusing here?
You shower, why would you?
I'm just look, I don't know who this person is. This person here showers once per day, okay? What are you confused by? You think this is too much or too little? What's the?
We have to consider the time.
No, because in Ireland or in most places it's the how many joules of energy you use. It doesn't matter over the time that you use it. Yeah. Yes?
I don't know, maybe I shower twice a day.
Okay, well then if it's no problem, twice a day, then multiply it by 2. So that's like 27 euros. So if you get an electricity bill of 100 euros, then 27 of it will be just from the shower. Yeah. The point I'm trying to make is that heat and water uses a lot of energy. That's just the point I'm trying to make. Yeah.
8.15 is for what energy?
That was the cue that we got. The energy needed to heat the water from 10 Celsius to 40 Celsius. For 65 litres of water, which is what you need for a shower, that's 8.15 megajoules of energy. And that's a lot. That's a lot of energy. Megajoules is million. Yeah. So, think about this. If the water, instead of being 10 at the beginning, so we went from 10 Celsius to 40 Celsius, that was 30, yeah? Suppose instead, let's see, the water was 20 at the beginning, and we go to 40. Then what's the difference here? It's only 20. Now, if that 30 instead was a 20, then this would be, a good bit smaller, wouldn't it? It'd be maybe about 5 megajoules or something like this. So you would actually save a good bit of money. You would save, of the 13 euros, maybe you would save about, 4 euros, 3 or 4 euros every month for a year. So what some homes nowadays do is the water that comes into the home at 10 Celsius, it goes very deep into the ground and then back up into the home. Maybe this is maybe 30 meters or something. And the water comes out at 20 Celsius perhaps. Now, of course, that's still too cold for the shower, but because you've made the delta T smaller, it means you've actually saved a bit of money because you have to use less energy to heat it up. So these are like the new modern energy techniques to be more energy efficient. And it's very, very simple. You just drill a big hole in the ground and have the pipe go down deep and up again, because the ground will be a little bit warmer than the air up here.
You need more the energy to drink the water.
Oh yeah, of course you need energy to make the hole. So in the beginning, you have to pay money to do this, but maybe after 5 years, you've saved more money than you paid to drill this. Yeah? Okay, let's have a look at another one now. Here we go. Loading. Come on, it's taking this so long. Oh, here we go. Right, here is another one, but I'd like you to try this one now. A block of ice begins at -10. How much energy do you need to increase it to -1? Got an answer there? What did you get? Was it? And what did you use for C?
2110.
Huh? C.
2110.
2110. Good. I didn't trick you here. So the C is different for the ice than it is for the water then. Huh? Okay. Continue? Yep. Right. An electric heater has a power of 3 kilowatts, and you use it to heat a room which is 10 by 10 by 5, and the room is 10 Celsius, and you want to increase the temperature to 20 Celsius. Take the density of air to be about 1 kilogram per meter cubed. How long will it take for the room to reach the desired temperature? So what's happening here, you've got a room, and it's 10 by 10 by 5 meters, and you have an electric heater, and the heater heats the room, and you want to know how long will it take. So the power of the heater is 3000 watts, the density is 1 kilogram per meter cubed. What else do you know? You know that you want to go from 10 Celsius to 20 Celsius. Yeah. So what formula do I need here? This is like my electric kettle example. Power equals work over time. So time equals work over power. And what's the work here? What formula is the work here? MC delta theta, and the power is 3000. Now the problem is we know this, but we don't know the m. So how can we get the m here? Yeah? Density equals mass over volume. Volume, not voltage. So that means the mass equals density by volume. So we can write this formula as density, volume, heat capacity, delta theta over 3000. Okay, so what's the density of air? 1. What's the volume here? 500. What's the C? I know the C, you have to look it up. Yeah. 1012. The delta theta and the power 3000. Okay, so tell me now what's the time? One 168 6.6. Okay. What's that, about 30 minutes? Divide that by 60. 28 minutes? Now, in real life, will it take more or less than 28 minutes? More, because what's going to happen is the room, of course, will lose energy, like through the window or the door or whatever, so it's losing energy, yeah. And not only that, in our picture we imagine the room is only air, but of course it's not only air, like you have other materials which need to heat up, like tables and carpets and walls. So it's going to maybe, instead of take 28 minutes, it could take 60 minutes because of windows and because of different materials and all this type of stuff. 28 minutes would be the quickest it could take if the room was empty and the windows were perfectly closed and all of this stuff here. But of course, you know that's not real life. Like even like under the door, heat will go under the door. You know. Okay, continue. Right, here's another one to try. I think this may be. Oh no, there's still another one after this. A physics student is making a latte. He mixes 200 grams of hot milk at 27 Celsius to 50 grams of hot coffee at 80 Celsius. And I say, imagine the coffee is just like water. What is the final temperature of the deliciously warm, steamy latte? So you have your milk and your coffee, and you mix it together, and you want to know what's the final temperature. So let's draw this to see what we got. How much milk do we have? We have 200 grams. 200 grams of milk. And what's the temperature? It's at 27. Then you mix in 50 grams of coffee. So you pour the coffee in. Yeah. And then I'll just draw it on the top. You have 50 grams of coffee at 80 Celsius. And then you mix the two together, and of course the temperature will be less than 80, but more than 27. And my question is, what is this temperature? So let's calculate it. Why do I have two blacks here? It annoys me. I want to have a red one. Well done. No. Doesn't matter. Okay, so let's calculate this. So it's important for these mixing questions that you clearly understand who is gaining and who is losing energy. So let's start with the milk. Will the milk gain energy or lose energy? Yeah, because the milk starts off cold and you mix in something hot. So the milk will gain energy, and the coffee will lose energy. Now the key here is understanding that because of conservation of energy, the energy which is gained by the milk, equal to the energy lost by the coffee. And they both start at 27 and 80, but they both finish at some temperature we'll call X then. Yeah? Okay, so what is the energy gained by the milk? So that's M. What's C for the milk? 2,850. And what's the change in the temperature for the milk? The milk goes from 27 to X. X minus 27, good. And this should equal the energy lost by the coffee, which will be M C, which is 4181. Oh, thank you. 0.05. C, now the coffee goes from X to 80. So, 80 minus X, because it goes from 80 to X. Because I said in the question, approximate the coffee as water. Because when you think about coffee, all it is hot water with a few coffee beans in it. It's kind of like water. Okay, what I want everybody to do now for me is to solve this equation. So you'll have to first...
The coffee goes from X to 80.
The coffee goes from 80 to X. It starts at 80 and it drops down to X. Whereas the milk starts at 27. Yeah, they both finish at X. But the reason I'm saying it differently is because you must understand that the X is smaller than 80. So I only care about the change. In other words, I don't want to have negative numbers here. So here the X is somewhere between 27 and 80. So I need to write the X before the 27, so this can be a positive. But here I need to write the X after the 80, so that this can be still a positive as well. Okay, I want everybody to solve this. You might want to multiply this first and multiply this first. Okay, so see what you get here when you try to solve this. Tired, Bruce? Tired? Eyes tired, yeah. Getting answers? Yeah. 41. That seems like the right answer, doesn't it, for a latte? 41 Celsius? Yeah? I think so. Okay. Continue. Is that a yes? continue. So, how much warmer would a 10-gram lead bullet travelling at 100 meters per second be when it strikes a wall? So I'm sure you've seen action movies before, right? And I'm sure maybe you've even seen a scene where somebody gets shot and it's cold outside and you can see the steam coming off their dead body. I'm sure if you think about a movie you've seen, maybe you've seen this. No? No? You can't picture this? So, when a bullet hits someone or something in a movie, it actually makes a lot of heat. So you can see the steam coming off of it. Yes. Which movie are you thinking of? Do you have one in mind? You remember seeing that? Yeah, okay. Do you know any movie, can you think of any movie where you've seen this?
Wonder Woman.
I don't think that was gruesome enough to have such details in it. No. Anyways, you can believe me anyways when I tell you, when a bullet hits something and it's stopped, it actually produces a lot of heat. Because what's happening is the bullet here has kinetic energy. But when it hits something and stops, what's happened to this kinetic energy? It gets turned into heat. Because it has to turn into something. So the kinetic energy here turns into heat energy here. Yeah?
Only heat energy.
And sound. But mostly heat. Okay, so let's calculate what happens here. So the bullet is 10 grams, traveling at 100 meters per second. So the kinetic energy is a half mv squared. And what should that equal? That should equal mc delta theta. And you realise, actually, it didn't matter what the mass was, because what happens here, they cancel anyways. So I really want to know what the delta theta is. So I can say the delta theta is v squared over 2c, which is 100 squared. And now what is this c for lead? It's a lead bullet. It's 129. Now nowadays bullets aren't made of lead, but in the old days they were made of lead. 129. I don't know if you've ever heard the expression in movies, eat lead. Have you heard this one? No? You've heard this one, eat lead? Bullets used to be made of lead, so this is why they say eat lead, as in eat bullets, as in I'm going to blow your head off. Okay, what do we get here for the delta theta? Should be a pretty big number.
3.38.8.
What is it?
38.8.
38.8 Celsius. Okay. Now that's the answer. Now maybe we would like to know what is the final temperature of the bullet, whereas this is only the temperature increase. So if we wanted to know the final temperature, I'll have to tell you the starting temperature, wouldn't I? So temperature at the end would be the temperature at the start plus 38.8. Let's estimate this. What do you think might be the starting temperature of the bullet? What temperature might it start at? Cold. But it's only cold because it's a good conductor. What temperature would it actually be at? Yeah, well, you can think about this. Where was the bullet before it was in the gun? Yeah. In other words, it should be at room temperature. Because maybe it's in your pocket or on the table or whatever. So what is the room temperature? In Ireland, what is room temperature? We're a little better than that. I'd say maybe about 20 or 19. So we'll say 20. So that means the temperature at the end will be actually a steamy 58.8 Celsius, which is pretty hot. 58.8. Yeah? Okay. This one's okay? Yeah. There is another example of this one here. Remember with the waterfall? This is 100 meters, and you have 1 kilogram of water here. And what energy does the water have up here? Potential, MGH, yeah. But it no longer has potential at the ground. And the kinetic energy it hasn't changed, because the speed here and the speed here, they're the same. So that potential energy, we said, turns into heat. So if we do a quick calculation here, MGH is equal to MC delta theta. Now what cancels here? The M, so we don't need to know what the M is. So the delta theta will equal GH over C, which is 4181. Now let's just say, to make it easy, G is 10 and H is 100. So that would be 1,000 over 4,000 roughly. So that's roughly 0.25 Celsius roughly. So it means for the waterfall, the difference in the temperature at the top of the waterfall and the bottom of the waterfall is 0.25 Celsius, which you could actually measure if you had a digital thermometer. You could actually see the difference in the two temperatures then. Yeah. This is the experiment that Joule did about 100 years ago. Okay. I think that was the last example. Yeah. So just for a couple of minutes, I just want you to have a look at the question in the workbook, and then we'll start the next lesson here. Where'd my pen go?